Joshua Patton. This is Ravi Patel, and this is Rich Poole. So I'll start out by the first step of the design process was defining a problem, and our problem was two reasons that we selected this as our project choice. The first is that there are huge garbage patches in all of the oceans in the world, the largest being the Great Pacific Garbage Patch, which is about twice the size of Texas. And 90% of that garbage patch is recyclable plastic that could be used for various things, such as turning it into 3D printer filament. The second reason is that the filament, as is extremely expensive. It's about $43 for a spool of, or a 2-pound spool of 3D filament. But you can't print very much with 2 pounds of filament. So, anyways, so if we were able to implement something like this in schools like our own, you'd be able to cut down the cost of running the 3D printer so that a lot more students would be able to actually use the 3D printer that the school purchased for them, instead of how it is now where we can print very few things and only for special occasions and stuff like that. So.
All right. The next step was to justify what we were trying to do here. First of all of the plastic pollution that is out there, it's harmful. It hurts people, animals, the environment, everything. Speaking to the cost of 3D filament, it's really expensive. And like Josh said, it's hard to run a 3D printer in a school without a really large budget, and that's not what a lot of schools have. So doing something like what we're trying to do here and recycle bottles into 3D printing filament would help a lot in that aspect.
The next step was researching the problem. During the initial stages of research, we did patent research, but we were unable to find any patents for the product itself. But we found similar products such as the Filabot, the Illustrator, and the Filamaker, namely. However, these products use 3D pellets instead of plastic, or shredded plastic, to make the filament. The only one that implemented a mechanism of reusing plastic was the Filamaker, where you can reuse failed prints to extrude plastic. However, the Filamaker is costly originally because it costs about $1,000, but it's overall the lowest because you can reuse failed prints. That was so that you can save money on the filament. The next step, what we did was we had to interview somebody to get the constraints and the criteria. The person we interviewed were Mr. Breed and Mr. Keel over here at Skyline. And from their responses and from looking and researching about the products, we came up with criteria such as recycles, 3D bottles, melts it, and extrudes type 1 and type 2. Type 1 is similar to ABS plastic, and type 2 is similar to PLA. Different 3D printers use different plastics. And we rated each of the products that we found online using the constraints and ours to see what part we brainstormed individual parts to use as different parts in our system, and we did a decision matrix for each of the part using the constraints shown on the PowerPoint, and we used the best ones in our actual product.
All right. Next was prototyping our system and trying to get everything to work. So there were two main components here. There was building the physical system itself and then programming. And the programming was mainly to control temperature automatically, so we didn't have to sit there and turn a switch on and off. But for the build itself, to get everything that we needed, there were quite a few trips to Lowe's, and we ordered a few things off of Amazon, like our nichrome wire, which was our heating element, and we wrapped that around our extrusion pipe or two. And then for the construction of the system, there were a lot of man hours spent both in and out of school. There was time in class, time out of class. It took a long time. And then, of course, there was testing, and that was trying to get everything to heat up when we wanted it to heat up, however much we wanted it to, and a lot of trouble came with the auger, actually, to get it to extrude properly and with enough torque to move all of the plastic that we're dealing with. And for the programming aspect, the biggest thing I would have to say was having to relearn the programming language that we learned in the third year class, digital electronics. There was quite a few things that I had forgotten and we had forgotten. Then there was writing, and the full program is actually over on the side over there. That took a lot of man hours as well, both in and out of class, just like building. And then troubleshooting, that was both physical and in the coding itself, because when you're dealing with as many wires as are down there, if you have any loose connections anywhere, something's bound to go wrong. And then, of course, if I type anything wrong, it wouldn't work at all. And then that process just kept going over and over again until we finally got the program to work properly. Now, for testing of what we tried to do here, there were two big tests. There was the testing of heating, which is in that table right there. And what we did is we wanted to conquer the problem of measuring our temperature, because the biggest thing was, where were we going to put our temperature probe? Because for a long time, we thought that the only place that we could place it was on the inside of our tube, and that caused a lot of problems. So what we did is we came up with this test here, and over a 30-minute period, every 2 minutes, we took the temperature of both the inside and the outside of our extrusion tube, and then we plotted it on a graph. And as you can see, there is very, very little difference. So ultimately, we decided to place our temperature probe on the outside of the pipe and adjust slightly for the temperature difference that there was, and we rolled with that. And then the other large test that we did was the actual melting of plastic, and that took, well, the melting and extrusion of plastic, and that took quite a while, because with our auger, what happened was it's not quite long enough, I guess, and to test the extrusion of the system, what we had to do is we had to put plastic in the funnel, and we would push it down and allow it to melt, and then we would push it through into the auger with a screwdriver, and that was pretty tedious, and it took a long time, but we were successful in melting and getting the plastic to not quite extrude, but get to move through the system. We never got it to actually extrude though, sadly. Okay.
So, because of the weather and because of not enough time, we did not have enough time to finish the product. But these are some things that we could improve on, such as mainly a shorter pipe to fix the problem with the auger, and the shorter pipe will allow for a lower thermal mass, which meaning it'll be easier to heat up and cool down. So if something goes wrong with the system, you can react to it faster than right now.
One of our huge problems was we used a furnace cement on the outside of the pipe and funnel. And the furnace cement was very, very brittle and caused, we had to put a base layer on it to prevent the wire from, the nichrome wire from shorting on our pipe. And the base layer underneath it ended up cracking where we couldn't see it. So we would either have to chip all of the furnace cement off and redo, which we didn't have enough time to do, or we would just have to suffice with only using one of the two wires that we had, which caused us to only be able to melt type 2 plastic instead of both type 2 and type 1.
Another thing that we could have definitely improved on was